Okay, let's get started. I assume this is everyone's first class of the semester, so welcome back. As you probably figured out, this is CS 206, Evolutionary Robotics. If you're not signed up for 206, you're in the wrong room. Now's the time to leave. No, we're all in the right place at the right time? Okay. So what we're going to do today is mostly we're going to do a lot of logistics, how the course is put together, what I'm going to expect from you, and what you can expect from me as the instructor, and Kevin, who's the TA, who's here just in time. That's Kevin there in the back. So again, we're going to talk mostly about logistics today. We might get into a little bit of the content if we have time. Before we start talking about CS 206, let's take a step back and talk about the computer science department in general. This season, we are hiring 5 new professors into the computer science department. As you probably know, we're a small department, so that's basically going to double our size. We are now hosting a number of visitors. These are faculty candidates. There's going to be 14 of them over the next 6 weeks. So if I'm a little bit inarticulate in class, it's because I don't know who's coming and who's going. We've got a lot of visitors, which is good news for you because there's going to be lots of interesting people coming from all over the country and all over the world giving talks on different aspects of computer science. Our first visitor is here today, Iris Howley. She's visiting from Stanford University. Her area of research expertise is human-computer interaction, and she's going to be talking at 3 o'clock today on the 4th floor of the Davis Center about education technology. I think there will also be free coffee and snacks, so come and learn something and get a little bit of sugar or caffeine in the middle of the afternoon. Everyone's invited. The more the merrier. I'll put up the job advertisements as we go. Okay, so back to computer science 206. This is going to be the go-to point for you for the course, Blackboard. I think it's listed as CS 295, cross-listed, something like that. I apologize for that, but that is the course. It's either listed on your Blackboard as, CSIS 295 or CS 206. They're the same. This is where everything is listed. Okay, so the 2 main documents that are pointed to from the Blackboard site are the syllabus and the schedule. So let's start with the syllabus, and we're going to go through this together so we're all literally on the same page here. You'll find that most of the material in the course is hosted in Google Docs, which are linked to from Blackboard. Okay, so obviously we're here Tuesday and Thursday mornings. I apologize if you're not a morning person. I am. You'll notice also there's a link there to the schedule. We'll go through the schedule in a moment. I'm hosting 2 one-hour office hours, one on Monday at 3 to 4 and the other at Tuesdays 10 to 11. Something new for this semester is the office hour on Monday is not in my office. It's on Twitch. Twitch is this crazy website where millions of people go to watch other people play video games. There are different channels for different video games. There's a new channel now called Dr. Josh UVM, and if you head over there on Mondays 3 to 4, I will be streaming office hours from my office. So if you want to come and talk about evolutionary robotics in person, come see me on Tuesdays. If you want to ask an anonymous question in the chat window on Twitch, there's the time to do it. I will also record the live streamed office hours, and I'll put that on the schedule after the fact. So if a question does come up and you want to watch the office hours, you can go back and do so. First time we've done this, so we'll sort of see how this goes. Okay, those are my office hours. Again, Kevin's there in the back. Kevin, just put up your hand for a second. Kevin is going to be hosting office hours on Thursdays, 11 to 1 p.m. in 009 Mansfield House. That's the red building, which is just on the far side of the Voti parking lot. So you can go find Kevin there on Tuesdays if you have questions. Okay, I'm not going to read the description of the course for you, just to point out that throughout this course, we're going to be talking about autonomous machines. This should probably say autonomous and adaptive machines. All of the robots, or most of the robots that are out there in existence at the moment, are either autonomous machines, they're not adaptive. So industrial robots are autonomous. They do the same thing over and over again by themselves, but they can't adapt if something changes or something goes wrong. So there are autonomous yet non-adaptive machines that are out there. There are also adaptive machines out there that are not very autonomous, and those are the drones that are out there. So the drones are adaptive because there's someone somewhere driving them, and that person is adaptive to what they see the drone doing. The attempt in evolutionary robotics is to create machines that are both autonomous, no one's driving them, and they're also adaptive. They're able to continue their mode of operations as the world around them changes. That's the ultimate goal of evolutionary robotics. Okay, you're going to be conducting a major programming project. We'll talk more about that in a few moments. The textbook for this class is Floriano and Mattiusi's Bio-Inspired AI. It's on loan in the library. It's not a required textbook. So some of the selected readings, I will, again, post them here on Blackboard. You can go and take out the book and have a look at your leisure. There is also some supplemental reading that will be coming from, if I have it here, a book I co-authored a few years ago with Roel Pfeiffer called How the Body Shapes the Way We Think. Kevin, can you also put this on loan in the library? Come and collect it from me at the end of class. By the wonders of modern publishing, for every copy of this book that you buy, I receive $1. There are currently 47 of you signed up for this class. So that's $47 for me if every single one of you buys a copy of the book. So not too much financial incentive for me to get you to buy a copy. If you want to, of course, that would be wonderful. But it's optional. Okay, there will also be some additional readings that we will be drawing from the current literature on evolutionary robotics. Evolutionary robotics is an extremely young field. It only started in the early 1990s, somewhat different from calculus, which has been around for several hundred years. So a lot of the readings and a lot of the ideas we're going to talk about in this class have only been sort of written down in the last few years. They haven't appeared in a textbook yet. So you're going to get a chance in this class to actually read some primary sources, the actual original research manuscripts that report those ideas. And again, we'll talk about that when we get to it. Prerequisites for this class: you need to be both a junior and have programming experience. If you're missing one or both of those, come and see me after class. Okay. Again, there's a lot of coding in this class. And you're going to get a taste for the coding this week. We're going to talk about the first assignment, which actually starts today. And that first assignment is due a week from today. The reason I assign the first project, the first assignment right off the bat, is so you can get a feel for whether this class is right for you. If you find the first assignment to be relatively painless, you're probably in the right place. If you find that you're struggling with assignment 1, come and talk to me and we'll decide whether this course is right for you. Okay, everything in this class, if it's submitted 1 day late, 25% off, 2 days late, 50% off. If for some reason you have to submit something more than 2 days late, you don't need to. Okay, again, as I mentioned, there's a lot of programming in this class. The spine of this class, so to speak, is going to be 10 programming assignments. And over the span of 10 weeks, we're going to do 1 assignment per week. These assignments are cumulative. So if you don't manage to finish 1 assignment, you need to finish that assignment before you move on to the next one. So this is like math class or any other class you've had where homework is cumulative. Do not get behind. It's very hard to dig yourself out of a hole once you do. So stay on top of the weekly assignments. Okay, there are also a number of quizzes. So every Tuesday and Thursday night at 11:59 p.m., there is a short multiple choice quiz that's due for you on Blackboard. If you come to lecture and you do the readings, it should take you about 5 minutes. It's just sort of a prod to keep you on top of all the lecture material and the readings. So your first quiz is due tonight at 11:59 p.m. When I get back to my office after class today, that's when I post the multiple choice quiz. So you can do it any time from about an hour after class until midnight tonight. Okay, so as I mentioned, you've got these 10 one-week programming assignments. that will leave you about 4 weeks at the end to do a final project. When you finish the 10 programming assignments, you will have your own evolutionary robotics simulator running on your laptop, and you'll be able to run a simple evolutionary algorithm to evolve a simple robot to do something simply. You're going to then take that and elaborate it into a more complex robot, or a robot that's operating in a more complex environment. You might take the single robot and turn it into a swarm of robots. You might find that you're interested in the evolutionary side of things in this class, and you want to elaborate the simple evolutionary algorithm. You might want to take the neural model that's sitting inside of the robot and elaborate that. It's up to you. And again, we'll talk about things that students have done in the past, and we'll kick around ideas for final projects a little bit later on. Okay, 5% of your grade is also participation. So at the beginning of class, I will just pass around an attendance sheet. Just sign your name to the attendance sheet and pass it on to your neighbor. If you come to class late, no problem. Just make sure that you come up to the front at the end of class and sign the attendance sheet. You can miss up to and including 3 classes. If you find for some reason throughout the semester that you end up missing more than 3 classes, come and talk to me and we'll figure out something to do about that. Okay, that's everything to do with the nuts and bolts of the course. Any questions? No? Okay, so let's go back to the top and have a look at the schedule. Okay, so the course is broken up into a number of themes. So the first 3 classes is going to be sort of logistics and introduction and history. And then the second section called tools of the trade are going to be all the sort of bits and pieces that make up an evolutionary robotics experiment. Third theme will be a more detailed history of the course, some of the initial ideas and experiments. The next theme of the class, which is relatively long, is open problems or challenges in the field. As I mentioned, evolutionary robotics has only been around for 20, 25 years. There's a lot of wide open questions that nobody has a good answer to, and we'll talk about what some of those issues and challenges are. We'll then have a pair of lectures on collective or swarm robotics. And finally, we'll end with evolving bodies and brains. One of the things that sets AI and learning technologies apart from evolutionary robotics is that in evolutionary robotics, most of the experiments were trying to optimize or automatically improve not just the brain of the robot, but its body along with it. Right? Learning algorithms, as the name implies, are tuning up the brain of a robot or a computer. Evolution is not restricted to the brain. Evolution sculpts organisms, bodies, and brains together over evolutionary time. And we're going to spend a fair bit of time talking about how to get your evolutionary algorithm to improve not just the brain of your robot, but also the body. Okay. Okay, you'll notice there is links here. So I posted the lecture slides for today and also for Thursday. The links are there also for the reading. I'm also taping the lectures live. When I get back to my office, I will take the taped lecture, upload it to YouTube, and when I do, I will then link to it from here. So if for some reason you find that you're missing class, or you want to go back and listen to me explain another concept again, you can always go back and watch the video lecture for that day. There's also a YouTube playlist of all of the lectures from last year, and I'll link that on the schedule here somewhere as well, so you can go and watch those as well. Okay, you'll notice that assignment 1 is now live. And it is due next week at 11:59 p.m., so next Tuesday at 11:59 p.m. Next Tuesday I'll talk about assignment 2, which is due the following week, and so on. There are a couple of grad students in the class. Grad students, can you put your hand up? We've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, a fair number of grad students. You are going to be doing 2 assignments every week rather than 1 assignment. So obviously assignments 1 and 2 are now available. Grad students, your assignments 1 and 2 is going to be due next Tuesday. So far so good? Okay. Okay, so let's move on to a little bit of content before we do a little bit more lecture. I don't expect that all of you are going to go on and find a career in evolutionary robotics, but as most of you know, robotics and AI is very popular at the moment. Robotics and AI, since its beginnings in the 1950s, kind of goes in and out of fashion. It's sort of tongue-in-cheek known as the AI winter or the AI high summer. We are now enjoying another AI high summer. It's back in fashion. There are a lot of interesting jobs out there in AI and robotics. Again, not all of them are in evolutionary robotics. I hope that a lot of the concepts and ideas and experiments that you experience in this class might help you find an interesting job in AI and maybe robotics. I want to talk about a particular student for a moment, Nick Cheney, who grew up just down the road in Essex Junction. He was an undergraduate here and took this course 4 years ago. After graduating, he went to pursue a PhD at Cornell University. And at Cornell, he was funded by a specific grant from NASA to prototype or use evolutionary robotics techniques to prototype a new kind of robotic probe, and we'll have a look at that now.
We're investigating how to use...
Let me see if I can get the audio for you.
These really novel, tensile, soft, compliant, sort of more biologically inspired robots.
Perhaps. Okay, I will narrate this for you as we go. So this is a project being developed at NASA Ames,
really novel,
which is
tensile,
NASA research, one of their
soft,
NASA research
sort of
facilities in Silicon Valley, and they're trying to evolve a particular kind of robot known as a tensegrity robot. Has anybody heard of tensegrity structures before? This is an idea that actually comes from architecture back in the 1970s. If you look carefully, you'll notice that this robot is made out of a number of rigid rods, and the tip of pairs of rods are connected by a single line here. These are sort of springs. And if you look very carefully as this robot moves, let me back up a little bit.
More biologically inspired robots to explore.
If you look very carefully, you'll notice that no pair of rigid rods is ever touching one another. So this is a very interesting structure from an architectural point of view, and also now from a robotics point of view. It's very flexible, but also quite strong. So if you take each one of these rods, and in the middle of the rod you place a motor which can shorten or lengthen the rod, you get a moving tensegrity structure, or a tensegrity robot.
Today we're going to be looking
now,
at
why would NASA be interested in building a robot using this kind of structure? Why not stick with their standard wheeled rovers?
Weight and space.
Weight and space, right? So it's quite light. One of the amazing things about a tensegrity structure is if you were to grab one, it would actually collapse into a bundle of sticks. And if you were to then toss it out of another device and drop that onto a planetary surface, it would bounce back into its original shape. So that's of clear advantage to NASA. The biggest challenge that NASA faces is a hot landing, right? You've got this very expensive machine that's taken a long, long time to get to Mars or Titan or wherever it's going, and you want to make sure that the very delicate scientific instruments on board are not damaged during landing. So in this simulation here, imagine that this sphere is the bundle of scientific instruments that NASA wants to send to wherever.
Today we're going to be
looking at
what we call our Super Ball bot.
If you watch when this simulated robot
that we're designing that is able to both land on a planetary surface, absorbing impact.
The acceleration and deceleration of this sphere is relatively mild, even when it's moving over rough terrain. So these tensegrity structures are very attractive to NASA for lots of reasons. The problem with a tensegrity robot is how the heck do you control it? Right? A wheeled rover is pretty straightforward. You put it on the ground, and if you want it to go forward, you spin the wheels forward. If you drop a tensegrity robot on the ground and you want the tensegrity robot to move forward, which subset of these rigid rods do you shorten and lengthen to move in a particular direction? It's very anti-intuitive to figure out how to do this, so that's where evolutionary techniques become very advantageous. Right? Evolution, through trial and error, can figure out how to move one of these devices. Let me speed up this video a little bit.
It's protected from impact forces of landing by the elastic absorption of energy.
And we'll get to some actual locomotion here. So here's an evolved tensegrity structure. So after a lot of evolutionary trial and errors, they've been able to figure out, or evolution has been able to figure out how to lengthen and shorten these bars to move towards this target cube that the investigator will keep moving around. So this is an actual evolved tensegrity robot. No matter where it falls, it will always move towards.
And eventually the good ones get better and better, and out of all the thousands of bed controllers, you actually evolve a few good ones.
One of the interesting questions is how does
it's also good for moving over rough terrain. Doesn't seem to have any problem with that.
On the surface of another planet. And so this was an initial first robot like we're designing here.
So you can imagine actually putting 4 or 5.
And finally, we could take a swarm of them, and each one might have its own target that it's moving towards, and off it goes.
Even hundreds all going at the same time.
NASA's obviously interested in these kinds of things because they're relatively cheap. It might be much less costly to build a tensegrity robot than one of these wheeled rovers, and it would be great for NASA if they could develop, send not just 2 wheeled rovers to Mars, but maybe a bunched up bundle of these things, maybe a dozen or 100 or 1,000, and if even 30 or 60 or 90% of them break or something goes wrong on deployment, even if 10% of them keep going,
we're currently designing that target in mind. Is that how would you build a system like this that can deliver a 75-kilogram payload to the surface of Titan? But in terms of its potential,
so that's not the history of evolutionary robotics, but one possible future of where it's going, and hopefully it gives you sort of an intuition for why these evolutionary methods might come in handy. They work well in robotics domains that are non-intuitive. It's not straightforward for an engineer to figure out how to sit down and program the robot to do X. We're going to try and take a step back and instead of program the robot directly, create an evolutionary algorithm which through trial and error is going to figure out how to get the robot to do what the engineer wants the robot to do. Sound good? Okay. So Nick is actually around for the next few weeks, but he's off to NASA Ames. If you happen to see him, you might want to ask him more about this particular project. Okay. So again, you just saw one evolutionary robotics experiment. All the evolutionary robotics experiments that you're going to see in this course have 4 basic elements. We're going to go over them now. If you forget everything from this class when you finish with it, or this course when you finish with it, I hope you'll remember these 4 basic building blocks. If 30 years from now your elderly Professor Bongard emails you, or whatever exists 30 years from now, and asks you, what are the 4 basic ingredients of evolutionary robotics experiment? You're going to answer, an evolutionary robotics experiment is made up of a task environment, a robot, an artificial neural network, and an evolutionary algorithm. So obviously we need a task environment. That might be a virtual environment, which you're going to be working with in this class, or a physical environment, and obviously we want our robot to do something in that environment. We obviously have the robot itself, and inside the robot is a neural model or artificial neural network. And all of the artificial neural networks that you're going to see in this class, they come in lots of different shapes and sizes and flavors, but they all share one thing in common. They grab all the sensory input that's arriving at the robot. They transform that sensory input in some way. They might combine it with memory or internal state, and they then output signals to the robot's motors. Not unlike your neural network collects data from your senses, transforms it somehow, and sends signals to your muscles. An ANN is basically a function that transforms sensory input into motor outputs. And what most evolutionary algorithms that you're going to see in this class are doing is tinkering with or changing that transformation. The moment an evolutionary algorithm makes a change to an ANN, That means the new robot is going to respond differently to the same sensory input. Okay, we're then going to wrap these three ingredients, environment, robot, and ANN, in an evolutionary algorithm, which is going to tinker with the ANN and may also tinker with the robot's body itself. Okay, so again, just to solidify this idea, I'm going to show you a snapshot from another evolutionary robotics experiment. This is one of my own from a few years past. What you're seeing is a series of snapshots during an evolutionary algorithm. An evolutionary algorithm is basically a lot of trial and error. I'm showing you all of the successes, and I'm just skipping over all the failures. So for every success here, where the robot manages to grasp this blue object, there's 100 or 200 fumbles. But watching all of these successes one after the other, you can sort of see what an evolutionary algorithm does, which is, in this case, it's tuning up the ANN of this robot to get better and better at X. What is X in this case? What do you think I asked the robot to do?
The blue block on its back?
To put the blue block on its back, right? I had to tell the evolutionary algorithm how to measure each robot and determine how good the robot was doing at that task. What do you think that measurement was that I gave to the evolutionary algorithm? This is all automated, right? The evolutionary algorithm is figuring out how good the robot did. What do you think the measurement was that I gave to the evolutionary algorithm to determine this? Yes?
The location of the blue box relative to the point on the back that you want to leave.
Absolutely, right? So there's a little sensor here. This is actually a light sensor, which measures the amount of light. And this blue block, although it's not drawn in the visualization here, is a light source. It's a light bulb, if you like. So it's pretty easy for the evolutionary algorithm to know how well the robot is doing, how much light falls onto this sensor. That's it, right? So the evolutionary algorithm is playing through millions and millions of these robots, and it keeps the ones in which the light sensor registers more light and throws away the robots that register less light. And the robots that survive this process, the evolutionary algorithm takes those robots, makes a copy of them, and when it copies them, it makes a slight mistake, or it tweaks some part of the artificial neural network so that the new robots, the child robots, now behave slightly different from the parents, and some of them manage to grasp this object and lift it a little bit better, a little bit faster than their parents. Rinse and repeat. Right? The basic algorithm of biological evolution and evolutionary algorithms is pretty straightforward, right? Trial and error with slight random modifications. Okay, so that was actually part one of this experiment. Part two is that right at the end of this short burst of evolution, when the robot successfully manages to grasp and lift the object, there's some light threshold. I told the program that if light ever goes above this threshold, I want you to make the robot's task environment a little bit more difficult. So right at the end here, this very last robot, at this point, this robot managed to get light above this threshold, and the evolutionary algorithm then changed the environment a little bit, which made things harder for evolution, and had to sort of backtrack a little bit, re-evolve, and continue, which you're going to see in part two here. So now in part two, I'm now just, again, showing snapshots during this evolutionary algorithm, and I'm showing you the successes right at the end before the environment is made slightly more difficult. How is the evolutionary algorithm making the task environment more difficult?
It's distancing the block away from the robot.
Absolutely, right? So when it grasps and lifts the object before, now I move the object slightly further away. It does the exact same thing again. Light levels drop, and evolution has to re-evolve robots until a new robot gets above that light threshold, right? Rinse and repeat. How's our robot doing?
I like when you try to throw it behind him.
When it throws it behind it, right? That one's pretty good.
It's like he's even afraid of the block at this point.
He's afraid of the block. Just grab it and get rid of it as quickly as possible. So there's a running joke in evolutionary robotics that evolved robots are like teenagers. They will do exactly what their parents asked them to do, but in a way that we didn't want them to do it retrospectively, right? The robot says, hey, listen, you wanted light. You didn't say anything about grasping and holding the block, right? So this is kind of a good thing and a bad thing about evolutionary robotics. We want evolution to discover these novel or interesting ways of doing whatever we wanted the robot to do, but it's also sometimes a disadvantage because some of those robots may not do it in the way we wanted it to do it, right? I don't suggest anyone gets on an airplane in which the control software for that airplane has been evolved by an evolutionary algorithm, right? It may maximize whatever the fitness metrics are, but maybe not in a way that would be comfortable for humans. This is one of the open challenges in AI and robotics in general, right? Parents face the same thing with teenagers, right? You want your teenager to grow up into an autonomous adult, but again, you'd hope that they would sort of do things in the way that parents or humans in general would prefer the teenagers, or in this case, the robots, to do it, right? So autonomy is tricky, right? You're giving someone or something the freedom to decide how to achieve some task you've set for the machine, but you're a little worried about how it might do so. Okay. Tell me a little bit more about this robot. Again, the fitness function, or the measurement I gave to the evolutionary algorithm, is just maximize light. What else is this robot doing, aside from maximizing light?
It's slowly crawling towards the block in like an attempt to find a distance from the block that is perfect.
Okay.
And it keeps slowing down, but I think it figured out that that's not going to work.
So the crawling is not going to work, you mean?
Yeah, like at first it was like rushing at the block, and then it's really slowing down now.
Absolutely, right? So sometimes it goes quickly, sometimes it goes slowly. I didn't say anything to the evolutionary algorithm about speed, right? That doesn't really matter too much.
It now knows to let go of the block when it's above its head.
Yep, again, because that's fine. It maximized light for a while, and then the block fell off. What else can you tell me about this phylogeny, or this sequence of robots that you're seeing? What's happening over evolutionary time as this experiment continues?
Kind of filters back and forth more often. It doesn't sort of just dive in straight, sort of.
Okay.
Levels, kind of.
Yep, so it definitely tilts back and to the left and right sometimes not.
It's been swinging its antennas like around more.
Yeah, you'll notice that the antennae usually go in sync with the legs. This is kind of a subtle thing. Why? Now again, I haven't told you all the nuts and bolts of this experiment.
Is that just like the weight distribution of the robot? It's the best way it can walk in the environment?
Possibly. So we're going to spend a lot of time talking about legged locomotion and bipedal locomotion. When you run, you pump your arms in opposition to your legs to cancel torque about your long axis. It might be that doing that helps the robot stay balanced. It's not quite clear in this experiment. That might be a reason. Jack?
It could be used to like gauge the distance to the block.
It's possible, right? So that might be a good way to sort of figure out where it is and then grab it.
You evolved from the initial task when it first did it.
Absolutely, right? So remember at the beginning here, what does it have to do? All it has to do is reach out and grab and lift. So it already has evolved the ability to do this, and it just keeps repeating this pattern. So this is a very clear example of a biological phenomenon called exaptation. Mother Nature is extremely lazy. If she's come up with a solution that already works, and the environment around her changes, or the environment around the organism changes, then what Mother Nature will often do is exploit an existing adaptation. So in our reptilian ancestors, there were a number of bones in the jaw that help reptiles crush their prey. Over evolutionary time, as reptiles evolved into mammals, those same small bones were exploited or pulled into the inner ear, and they now form the stirrup and the whatever else it is the bones in your inner ear. Those bones now help mammals to hear. So those bones are an example of exaptation, and you can see this idea at work here. So the evolutionary algorithm has discovered closing and lifting, and it just keeps using that throughout the evolutionary process. This is, again, one of the fun things about evolutionary robotics, is often you see in one of these evolutionary runs, you see biological phenomena or evolutionary phenomena that we also see in biological populations. Yes?
Is there anything stopping our evolutionary algorithm from reaching a local maximum to the global maximum of efficiency?
Yes, so that's a great question. So the question was about local optima and global optimum, and we're going to spend a fair bit of time next week talking about that. So a local optima is just a solution that's good enough, but it gets you stuck. You're on top of a hill, and you can't get to the distant mountain, which is the global optimum, right? The best possible way to do things. I'm pretty sure, and you probably are too from watching this video, that these are all not the optimal way to get to the block, grab it, and lift it, right? What evolution, biological evolution is often known as a satisficer, not an optimizer. It will produce you something that's good enough, that satisfies what the animal, or in our case, the robot, needs to do in its environment, right? So again, another global or open challenge in evolutionary robotics is how do we make sure that our evolutionary algorithms don't just find good enough solutions, but given enough time and computational resources, find the best solution. No one yet has a good answer about how to do that. Okay, one final observation to be made about this experiment. You'll notice that the robot walks or crawls or hops or whatever you want to call it. That's a side effect of the fitness function. Right? The only thing that's in the fitness function that the evolutionary algorithm is using to measure the quality of each robot is light intensity. I didn't say evolve a robot that walks or evolve a robot that grasps the objects. So often the side effects of these evolutionary experiments are kind of interesting in and of their own right. Again, you'll notice that this robot doesn't always walk in the same way. So there's a lot of diversity in the solutions that evolution comes up to, which is kind of the opposite of exaptation. Right? Exaptation is a very conservative phenomenon in evolution where it tries to keep and maintain things that already work. But at the same time, evolution is often trying out lots of different things, and often diversity is a good thing for us, right? So when NASA is prototyping their tensegrity robot probe, they'd like to see all the different ways that the tensegrity robot might fulfill the mission, and maybe at the end, NASA engineers might say, that's the particular behavior we want. All these other ones are not quite what we had in mind. Okay. So again, just to give you a taste of where we're going, you're going to see a lot of evolutionary robotics experiments throughout this course. I don't expect you to remember the detail of every robot and every ANN and every evolutionary algorithm, but I do want you, as we introduce each experiment, to keep an eye out for these 4 basic ingredients. If you can sort of spot those 4 ingredients in each experiment and sort of understand how they work for that experiment, you're in good shape. Okay, so let's get back to logistics for a minute. Just a little bit about myself. I started out as a computer science undergraduate as well, like many of you, at McMaster in Canada. I went to go work for a year in Calgary, found out that industry wasn't for me, came back to academia. I went to go do a Master's of Science at Sussex University in Brighton. As I mentioned, evolutionary robotics is a pretty young field. It only started in the early 1990s at Sussex. So it was the only graduate program in the world at that time on evolutionary robotics. It was an interesting program because they admitted half computer science students and half biology students. The biology students had to take programming classes, and us computer science students, we were thrown into wet labs and had to do dissections and all that sort of thing. So we were all getting caught up on the same bulk of work, which is a basic understanding of computer science and evolutionary and adaptive systems. After my master's degree, I went to Switzerland for 4 years to pursue a PhD in evolutionary robotics. Later in this course, I'll show you some experiments from my PhD. Then came back across the pond to Cornell University, spent 3 years as a postdoc working with Hod Lipson. Hod Lipson is one of the founding fathers of evolutionary robotics. We'll see a lot of work by Lipson and his students as we go along. I was working on a project for NASA as well while I was at Cornell. We'll also talk about that NASA project in a little bit. And I've been here at UVM since 2006. Okay, let's talk a little bit about expectations. So what I expect from you is feedback. As you've already figured out, there's a fair bit of Q&A in lecture. Common sense, regular, not necessarily perfect attendance. We talked about that. Hard work. Some of the programming projects might take you 15 minutes. Some of the weekly programming projects might take you a lot longer than 15 minutes. I can't tell you which is which. It depends on your programming abilities. So the best advice I can give you is when the project is assigned, get started on it. Don't leave it for the night before. Okay, as I just mentioned, I expect you to memorize sort of key concepts, but I don't expect you to memorize every nitty-gritty detail of every experiment. There's a lot of room for creativity in this course, especially when you get to the final project. Self-learning is really important in this class. This is an upper year class. All of the coding that we're going to be doing in this course this year is in Python. If your Python's a little bit rusty, go take a Python tutorial. We're also going to be doing, in 3 weeks' time, we're going to be doing a lot of work in object-oriented programming. We need to build you need to build modular code so that you can modify it easily in the remaining weeks of the course. If you don't have experience with object-oriented programming, go find a tutorial online on that and brush up your skills on OOP. Okay. Positive attitude, I think that goes without saying. Okay, what you can not expect from me, and by me it's the royal me, meaning myself, and the TA, Kevin. You can't come to us and say, why is my program crashing? Kevin and I don't know either. We can't help you with that, unfortunately. I do, again, expect you to try and get everything installed on your own. I can't teach you Python, but Google can. There you go. Okay. What you can expect from Kevin and myself, we will help you with specific programming questions after you've sort of tried to figure it out on your own. This is sort of a holdover slide from last year. Last year, the programming projects were in Python and C++. This year, they're just all in Python. But if you've got questions about object-oriented programming in Python, you want to talk about it, we're happy to do so. Okay. And again, I'm happy to talk with you in office hours about conceptual issues. That's obviously no problem. Please ask any questions about clarifications about the quizzes, assignments, the project, and so on. As you've already figured out, there is no midterm or final exam in this class. Okay. Especially what you can expect in this class is an emphasis on concepts rather than specific tools, because specific tools come and go. There goes C++, right? I hopefully will be teaching this class 5 years from now. It'll probably be completely different, but the underlying concepts will still be there. So pay attention to the sorts of concepts that are introduced along the way, and remember the basics of the experiments or the tools that illustrated those concepts. Okay, so now we're going to spend a fair bit of time talking about the 10 assignments and exactly how this works. Again, you can find all of the assignments posted on Blackboard. They're under course materials. So I'm now going to actually walk you through how to do one of the assignments and submit it. Again, you don't need to remember everything because I'm recording the lecture. So if you go to submit your assignment, you forget how to actually do it, go back and watch the video lecture from today. Okay, here we go. So let's go back to Blackboard, course materials, and there's a folder there with assignments, and assignment 1 and 2 are already on there. You're going to be jumping around from a number of websites as we go, so I'm just going to sketch this out on the board as we go. We're starting at Blackboard. When you click on the instructions for assignment 1, that's going to take you to a Google Doc. which has all of the instructions for assignment 1. Okay. So it looks deceptively short, and the reason why is because there are links into Reddit, which is our next stop on the assignment trail here. Who's familiar with Reddit? Pretty much everybody now, I would imagine. Okay. You post content to Reddit. If people like the content you posted, they vote it up or vote it down. I host all of the assignment material in Reddit. And the reason why is because I actually host a course, an online course in Reddit called Ludobots. Ludo is Latin for play. So you're taking this course here at UVM, but you're going to be shadowed over the next 14 weeks by not quite 805 other students, but I think several hundred other students who are going to be taking this course along with you. They're going to be seeing the video lectures, and they're also going to be taking the course. They're going to also be doing the assignments, but they're doing it all completely in Reddit. So you guys have this part. Your online peers join you at this point. Okay, so let's go back to Google Docs for a moment. So there is a link. Let's see. Please complete the first assignment here. This link will take us to the actual first assignment in Reddit, which is called Connect the Dotbot. This has a number of instructions that you're going to follow. And what you're doing in Connect the Dotbot is going to another website that one of my students made that allows you to create your own robot and then evolve an ANN, evolve a neural network for this robot, all in browser. So this is just a way to give everybody a taste of evolutionary robotics before you even start writing any code. So there we go. I've done the first assignment in Reddit, which is create a robot and evolve an ANN for it. When I finish here, and again, this is all in the instructions, you're going to be asked to take a screenshot of your robot. So I'm going to take a screenshot now. And that should drop my screenshot right here. Okay, so I have proof that I completed this assignment. And if we go back to Reddit here, the next stop is Imager, which is this website which just easily allows you to upload images. So upload your screenshot here. So now we're at Imager. I take my screenshot, drop it in here. And when I do, it creates a link for me. So here's my link pointing to Imager. Copy this. Go back. I've gotten lost already. Let's go back to Reddit. Okay, so I'm working in Reddit on the first assignment, Connect the Dotbot. I've made a screenshot, step 8 here. I've uploaded my screenshot to Imager. And now I'm going to post my solution to Reddit. So I'm going to show to everyone else that I've completed the Connect the Dotbot assignment. So in step 12 here, I click on Submit Work for this project. And I take the URL that I have from Imager, and I copy it into my Reddit submission, and submit. And now I can see that in the Ludobots subreddit, Dr. Josh has submitted Connect the Dotbot. So I've now finished the assignment, I've gone back to Reddit, and I've made a post there. There's proof that everyone can see. The nice thing about posting this on Reddit is that other students can upvote or downvote your solutions. So I ask all of you, and I also asked all the online students to help each other. So next Tuesday, you're going to see 47 submissions rapidly appear on Reddit. If you have some time, go through the submissions of your peers, upvote it if it's correct. If it's not correct, if you see something in the screenshot that shows that your fellow student made a mistake, still upvote it, but leave a comment and a helpful suggestion. So I'm asking all of you to not just be students in this class, but also to be TAs. Don't give your fellow student the answer, but you might leave a comment saying, you might notice in your screenshot that the leg of this robot is at 30 degrees. It should be at 60 degrees. Where do you think the error might be in your code that's causing that to happen. Sound good? Hopefully other students will return the favor to you if your assignment isn't perfect either. Okay, so now I've got my solution here on Reddit, which of course also has its own URL. So now I'm going to copy this URL and go all the way back to Blackboard now, to the actual assignment. And in, in text submission, all you need to do to submit your solution to Blackboard is copy the URL that points to your Reddit submission, and then click Submit. So now you've submitted assignment 1 for the course. So the online students are going here and they're submitting their work on Reddit. They're obviously not being graded. You're working your way all the way from Blackboard down to Imager, posting screenshots of your solution, working all the way back again. Did I actually submit? Perhaps. Okay. All of your solutions are going to be posted. You're not going to be submitting code. Again, Kevin and I are not going to look at code. We're going to be looking at screenshots, and those screenshots are designed to allow us and also you to see easily whether there is an error in your submission or not. For the first few weeks, all you're going to be doing is posting images to Imager. Later, once your robot starts to move, you're going to be recording videos of your robot in action and posting those videos to YouTube. You take the resulting YouTube URL, plug it into Reddit, which gives you a Reddit submission. You, again, just post the Reddit URL into Blackboard. So lots of jumping around, but hopefully once you've done this a few times, it'll be pretty straightforward. Sound good? Okay, so I just talked about Connect the Dotbot. Let's actually go back here. In assignment 1, you're going to be doing the Dotbot project, but you're also going to be moving on to the next assignment in Reddit. So assignment 1 is actually made up of 2 Reddit submissions. The first one is Connect the Dotbot, and the next one is installing PyroSim, which I'll talk about in a moment. So when you actually submit your solution to Blackboard, you're going to be posting not 1 Reddit URL, but 2 Reddit URLs. So far, so good? Okay. So let's talk about PyroSim for a moment. This is going to take us again to another Reddit assignment. Here's PyroSim. The big issue for us this week is making sure that everyone gets PyroSim installed. So let's go to the PyroSim page. Okay, this is a robot simulator that I've developed, and it's posted on GitHub. How many of you have used GitHub before? Most of you, not everyone. That's okay if you haven't. Again, go watch a tutorial on Git or GitHub. This is a way to maintain code repositories. At the bottom of the GitHub page here is instructions about how to install PyroSim. And again, I want to make sure that everyone gets PyroSim installed this week. We have tested this for Mac and Linux. And if you have a Mac or Linux machine, it should take you about 10 minutes to get PyroSim installed and up and running. How many of you have either a Mac or a Linux machine? Just a few of you? Okay. The rest of you have Windows machines? Okay, so this is going to be the big challenge this week. I am a Mac person. Most of the grad students in my lab are either Mac or Linux people. So we've been trying our best to put together a Windows installation. So we're road testing the Windows installation. So again, especially if you're a Windows person, please start early on this. If you get stuck, email Kevin and myself, and we will try and figure things out. We may update the installation instructions here on GitHub. Hopefully, all you need to do is plan A, which is described here. Just a few steps. We're pretty sure for most Windows devices this will work. If this doesn't work for you, I've recorded a video tutorial here, which is Plan B. Plan B is to install a Linux virtual machine on your Windows machine. So you have your Windows machine, you'll have a Linux virtual machine running inside Windows, and inside your Linux virtual machine, we know that PyroSim works. It's not an ideal solution, but for the moment, it's Plan B. All right? If Plan A does not work for you and you're a Windows development guru and you find out a better Plan B, we would love to hear about it. All right? Yes?
Has anyone tried it with Hackintosh yet?
With which?
With a Hackintosh?
I don't know what a Hackintosh is.
Like a Macintosh virtual simulator on Windows.
That would be fantastic.
Okay.
If you can figure that out, we'll put that as an option as well. Again, if the installation of PyroSim goes well, it should take about 10-15 minutes. All of assignment 1 will probably take you about 20 minutes. So for the Mac and Linux people, you probably get a pass for this week. It's not going to take you too long to get through assignment 1. Unfortunately for the Windows people, you might spend a fair bit of time on installation. I apologize for that. There's not much we can do about that. Hopefully we can get all the installation headaches out of the way. If we do, as I mentioned, everything is in Python. All the coding you're going to be doing in the next 14 weeks is built on top of PyroSim. So hopefully if we get all that done, it should be smooth sailing for the rest of the course. You can just focus on the concepts and not installation headaches. Question?
Is Python 2 or 3?
I think it works for both. Sam, do you know?
It's 2.
2. Okay, all right, so we will stick with Python 2. If you have Python 3, you might need to install Python 2. I'll put a note about that, again, in the installation instructions here. Okay, not much we can do about this. We need to get this installed for everybody's combination of platforms and operating systems and so on. Start early, and we'll try and get through it. Worst case scenario, if you're still struggling with installation issues by next Tuesday, we will give an extension to anyone who's still struggling with installation issues. Sound good? Okay. Okay, I will give you a demo of what you should see when you do get PyroSim installed. Okay, when you get PyroSim installed and set up, and you run PyroSim, what you'll initially get is an empty virtual environment like you saw in those videos a few moments ago. So at the end of assignment 1, you're going to be finishing with an empty platform. And then in subsequent assignments, you're going to be gradually building up the robot, the artificial neural network, and then you're going to wrap the robot and its artificial neural network in an evolutionary algorithm in a few weeks' time. So we're going to do this very gradually as we go. Okay. Any questions about any of that? I realize it's a lot of moving pieces, but hopefully everything's described more or less step by step, and we should all get PyroSim installed and our virtual environments running. We're good? Okay, let's carry on. So again, as I mentioned, that's what we're going to be doing for the next 10 weeks. In the last 4 weeks, you can choose your own project. I will point you at that time to dozens of projects that have been done in the past. You can pick one of those and try and improve upon it, or you can come up with your own idea and try that. Here's a sample of things that have been tried in the past. Given the same evolutionary robotics experiment, so the same optimizer or evolutionary algorithm, neural network, and 8 hours of evolution. So what you're going to hopefully be doing at the end of 10 weeks, taking your laptop, setting up your experiment at night, leaving it to run overnight, and when you get up in the morning, while you have your cup of coffee, you can see what evolution has evolved for you. So given 8 hours of evolution, and 2 different kinds of robots, a quadrupedal robot or 4-legged robot, or a hexapedal or 6-legged robot. If each of those 2 robots got 8 hours of evolution, which one travels further? Is it easier for evolution to get the 4-legged robot to move quickly, or the six-legged robot to move quickly, given the same computational effort? Anybody have any ideas? Taking bets.
I would assume it's the four-legged one because it's less to account for.
Less to account for, right? So there's literally less moving pieces in the quadruped, which mean there's less things for evolution to tweak, and maybe it can do a better job. So that's a point perhaps in favor of the quadruped.
I would argue that the more legs, the farther it could go in a shorter amount of evolutionary time.
Why is that?
Just because it's a more rudimentary movement, because it's not going to fall over as easy. If you gave it 2 legs, I would argue that a 2-legged robot can move farther, maybe not in 8 hours, but if you gave it 16, its overall top speed would be greater than the other 2.
Absolutely, right? So a 4-legged robot or even a 2-legged robot has fewer things to optimize or evolve, but those things have a bigger challenge, which is balance, right? They fall over a lot. So evolution has to be much more careful with how it tinkers with the brain of a 4-legged robot or a 2-legged robot. So there are arguments in favor of the quadruped and the hexapod. We don't know, so in order to figure it out, you're going to do an experiment for 4 weeks. Maybe you do 30 8-hour runs, so 30 nights in a row. 15 of those nights you evolve the quadruped, 15 of those nights you evolve the hexapod. At the end of 30 nights, which one is traveling faster?
You could set up a point where it finds where they reach the same speed, so you can figure out how long it takes one to evolve past the other one.
That exactly. Is there a point where they cross one another?
Yep.
Absolutely. That might be another thing to determine. Okay, that's one possible experiment. Another experiment would be not to tinker with the body or look at 4-legged versus 6-legged, but look at the evolutionary algorithm. So we hand a fitness function to the evolutionary algorithm. The evolutionary algorithm takes that fitness function and measures the quality of the robot. So we can come up with a simple fitness function for locomotion, which is how far in inches or meters does the robot get from the point of origin. That would be a fitness function that would reward for locomotion. But what if we want a particular way of moving, a particular gait? We want the robot not just to travel quickly, but we want it to walk or trot or canter or gallop or pronk or tolting, which is another gait that's only exhibited by Icelandic horses. There's actually 6 possible gaits for a 4-legged organism or robot. How would you create a fitness function that selects for robots that move quickly but gallop? Not so trivial to figure out. That's a good sort of project for a 4-week period. Okay. Perhaps you want to look at not just the speed at which the robot moves, but how much power it uses. All the robots I've shown you so far are extremely energy inefficient. You, when you walk around, are extremely energy efficient. Could we select, or could we tell our evolutionary algorithm to select for robots that not just travel quickly, but also do so by using relatively little energy? Turns out that this is a tricky thing to do if there are 2 things or 10 things that we're asking the evolutionary algorithm to do. Because evolution might say, well, I can't optimize both, but I can certainly find one robot that travels really fast and uses a huge amount of energy. And I can also give you another robot that uses no energy, that's infinitely energy efficient by never moving, right? It can maximize one of these objectives and says to hell with the other one. Getting evolution to try and improve both objectives at the same time, tricky. And again, we'll talk about that in a little bit. Perhaps you want to put a laser rangefinder on the robot so that it can distinguish between different objects in its environment, and you evolve a robot that walks toward round objects and away from edged objects. So we want to create in this course, or in evolutionary robotics, robots that are both autonomous and adaptive, but we'd also, in the long term, like to try and create them to be increasingly intelligent. What does it mean to be intelligent? Well, a robot that just scampers around maybe is not that intelligent, but a robot that can classify move towards round things, away from edge things. Classification, being able to tell classes of things apart is pretty important, right? Distinguishing between friend and foe, tool and weapon, all sorts of things is an important part of intelligence. Maybe maybe you're more interested in AI than robotics. A project like that might be more for you. Okay, that's just to give you a taste for the sorts of things that you might pursue in the last 4 weeks of this course. Okay, that's all I have to say about logistics. Any questions about how this course is run? Okay, we've got a grand total of 10 minutes left, so now we will start to get into a little bit of lecture material. Before we talk about what robots are, let's talk about why we might study robots in the first place. The first answer to why study robots is obvious. They're super cool, right? Everybody's interested in robots. That's the first reason. Second reason is they could be extremely useful, right? So the engineering answer is we already have robots which allow us to build things indoors in a very efficient manner. It would be great to develop autonomous and adaptive robots that can help out in outdoor environments. And the way that robots have revolutionized manufacturing, maybe they would also help us revolutionize construction or fixing national infrastructure, or deploying solar or wind farms, or what have you. The top pair of images shows that this has already happened for manufacturing, right? Henry Ford, over 100 years ago, came up with this idea of mass production, so systematize the way that things are built. Whatever you're building, if it's motorcycles, for example, you have the worker do one small thing, and they do that same specialized task over and over again, and that helped bring down the cost of motorcycles and cars and all sorts of things over 100 years ago. So Henry Ford systematized that process. In the 70s, industrial robots came along and automated that process. Right? That obviously raises one important aspect of robotics, which is the ethical issue, right? So industrial robots put a lot of blue-collar workers out of work. We are now again back into the robotics and AI high summer. Is the latest round of robots and AI going to put white-collar workers out of work? We'll see, and again, we'll talk about that later in the course. Okay. Regardless of the ethical issues, industrial robots certainly are of huge economic value. They allow us to produce many more things faster and cheaper, which is a good thing from an economic point of view. Why hasn't this happened for construction? It's happened for manufacture. Why don't we have outdoor robots helping out at construction sites?
Dynamic workspace.
Dynamic workspace, right? So every single construction site is slightly different from the one before. So over 2,000 years ago, the Greek philosopher Heraclitus said, man never enters the same river twice. Right? The real world is always changing around us, and organisms have been evolving for millions of years to deal with that change. Right? We are all pretty good at adapting to certain changes in our environment. Industrial robots, or robots in general, are not very good at adapting. So even if we wanted very simple robots that just moved bricks around at a construction site, at any given construction site, they would have to change the way that they moved bricks, given the particular layout of that construction site. They'd have to adapt their brick moving behavior from site to site. We, as a society, do not know how to build that kind of technology, right? We've built these things, we've built the International Space Station, we've built very sophisticated technology, but at heart, all of those technologies basically do the same thing over and over again. That's not the case for robots that operate in outdoor and unstructured environments. That's the open frontier for robotics, and my hope obviously is that evolutionary robotics is going to be the answer to that challenge. We'll see. Okay, so that's the engineering answer to why might you want to study robotics. I find that interesting, but I find more interesting the scientific or intellectual answer about why study robots. In robotics or intelligence in general, there is no underlying guiding theory for intelligence. If you look at all the other branches of natural sciences, they all have sort of their basic guiding principle, right? So obviously biology has Darwinian evolution. At heart, that explains a lot of what goes on in biology. There's still a lot of interesting things to learn about biology, but they're all elaborations on the basic theory of descent with modification. Physics has Newtonian and quantum mechanics. What's the guiding theory in chemistry? If you take a chemistry class, Chemistry 101, what's one of the first things you start to learn about? The elements, right? The periodic table. There's a certain structure to all the elements that we found in nature so far. There is no periodic table or quantum mechanics for the understanding of intelligence. We do it. It happens in here somehow, but it's still very mysterious. There is one or several Nobel Prizes waiting to be won for someone or a team to come up with the guiding principle for intelligence. This is how Mother Nature did it in mammalian nervous systems. Here's how we can take that idea and do it with artificial neural networks. That's for me, one of the intellectually exciting things about robotics and AI. It's the Wild West. There is no guiding principle yet. The big discovery or big discoveries have yet to be made. The other thing that's interesting about it is it's, in my opinion, probably the most interdisciplinary thing you can study out there, right? Robotics doesn't sit comfortably in just computer science. It doesn't fit comfortably just in engineering. Robotics draws, and especially evolutionary robotics draws on ideas from lots of different fields. As you've already seen, it obviously is going to draw pretty heavily from evolutionary biology. It draws pretty heavily from neuroscience. How do we set up these artificial neural networks for our robots? It draws on cognitive science. So neuroscience is about the brain. Cognitive science is about the mind. So if we do evolve a robot that categorizes, runs towards spheres and away from edged objects, what is the algorithm that evolved inside that neural network to do it? Right? So we're going to draw on cognitive science as well. Maybe psychology. Biomechanics, so the way that animals and humans move and get around in their environment, how we pick up heavy objects. So the engineering, the kinematics, that's pretty important. We're going to spend a couple lectures talking about legged locomotion. Physics is pretty important. So the empty simulator that I showed you, that PyroSim simulation, sits on top of a physics engine. So in a physics engine, you define an object. You give that object a shape. So in this case, I define a cylinder. I define the length of that cylinder and its radius. I give it an XYZ, which is its initial position in that virtual environment. I also give that object some mass. And then I turn on the physics engine. And the physics engine will figure out how this object starts to move. If I put that object above the ground, it will fall and hit the ground. The physics engine is going to do that for you, but we're going to have to talk a little bit about physics once we start using physics engines to simulate our robots. Obviously, there's going to be a fair bit of computer science. We're going to do a lot of coding in this class. Robotics requires drawing on all of the branches of engineering. We're even going to see some chemistry in this class. Towards the end of this class, we're going to talk about soft robots. So 3D printers, at the moment, mostly can print things out of plastic, but 3D printers are coming that can print multiple materials. So imagine you can print a robot that has soft and rigid components, not unlike we are made up of soft and rigid components. Those 3D printers draw on some pretty sophisticated and state-of-the-art ideas in chemistry. So chemistry is also an important part of robotics. We're going to see a fair bit of math as we go along to try and describe our robots and their artificial neural networks. And we will also get into a little bit of philosophy. Right? If we start to evolve robots that are intelligent or pause and think about how to grasp the blue object before they actually do so, are those robots pausing and thinking about what to do next in the same way that we are stopping and thinking about what to do next? Do our little robots say to themselves, if I go forward and I go like this at that exact moment, I'll grasp the object. In that robot's internal monologue was the pronoun I. If I do that. Can robots be self-aware? Can they be conscious? Right? We're going to stray into philosophy from time to time as we go. Okay, I think with that heady subject, we will stop for today. We'll pick it up on Thursday. Remember that you have a quiz that's due on Blackboard at 11:59 tonight. Please get started on assignment 1, and I will see you Thursday morning. Thanks very much.